Countless galaxies populate the universe, each with billions of stars majestically spread out over tens of thousands of light years. However, a surprising number of these galaxies in the outermost reaches of the universe are peculiar. They appear so bright, yet so compact, that their nature was a complete mystery.
Less than 50 years ago, we found out there was a whole different kind of thing in the universe that we had no idea what made it go. And it was not merely some small event, but it was the most powerful single thing we found anywhere in the universe. If we, as astronomers, don't understand that, then we clearly don't understand much about astronomy.
Most galaxies in the universe derive the light we see from stars. They're made out of stars. There is a peculiar collection of galaxies called active galaxies, in which a large amount of light is produced by some strange and unknown process taking place in their centers. It's not definitely the light of stars, it's something else.
Generally speaking, in cosmology, we have two ingredients that are very important to recognize as the most important sort of cornerstones. One of them is data, and the second one is the laws of physics as we know them from laboratory experiments. It is quite striking that we are able to understand phenomena that happen at the edge of the universe in terms of these laws, and this is one of the wonders of astrophysics, basically.
From the moment the first strange object called a quasar was discovered, astronomers knew it was unlike any other object in the sky.
It is so different from all the other things we see in the universe, which are stars and exploding stars and galaxies. A quasar is something so different from all these things that it's totally mysterious, and scientists love mystery.
One of the mysterious things about them was that there were point sources. They appeared to the casual observer just like any other star in the sky. However, as telescopes improved and instrumentation improved, people started seeing that the quasars weren't exactly like stars. They didn't have the same size and shape on the sky as stars did. Instead, they started to look a little bit fuzzy.
Quasars were first discovered in the early 1960s by their radio emission, although most quasars are not strong radio emitters. At the position of these radio sources were stellar-appearing objects, which, because we at that time knew that stars were not strong radio sources, these couldn't be normal stars. They were called quasi-stellar radio sources, which has since been shortened to quasar.
One of the first quasars to be identified with a visible counterpart was 3C 273. Its spectrum was also very different from that of a normal star.
There was an observation of 3C 273, which was a very bright radio source. And people were able to locate its position very accurately. And Martin Schmidt took the spectrum of this particular object and found 6 lines.
And it was Martin Schmidt in 1963 who was first able to decode the spectrum of the quasar 3C 273 and find that the features that were seen in the spectrum were in fact the well-known features of the Balmer spectrum of hydrogen, the most abundant element in the universe, but shifted by 15% towards the red.
It came as an inspiration, essentially. There were in total 5 or 6 lines in the spectrum of 3C 273. And one afternoon, when I was sitting at a desk writing a manuscript about the observations, I realized that among those 6 lines, if I forgot about 2, that the others seemed to be regular in spacing and in intensity. For some reason, I started to make an energy level diagram on the basis of what I saw. I made a mistake in the arithmetic. I became slightly irritated and said to myself, but there is regularity there. In order to check that, I took the ratio of each of the lines I had under consideration to the Balmer lines of hydrogen, which after all are very regular. And suddenly it dawned upon me that this was a redshift of the Balmer spectrum itself. That was a shock.
So, what Schmidt had found in the spectrum was a red shift that indicated the quasar was moving at a tremendous velocity, approximately 15% the speed of light.
In this case, it's the frequency of the light from the quasars that we see being redshifted from us. That means that the quasar is receding from us. Now we take an observation of the Doppler shift of the quasar. In this case, we call it the red shift, since the light is, for quasars at least, is always shifted to the red. That means the quasars are always expanding from us. If we take this measurement and combine it with what we know about the expanding universe, we can derive the distance of the quasar from the Earth.
A redshift of 15%, which, if interpreted as due to the expansion of the universe, corresponded to a distance of the order of 1 billion light years. Now, the extraordinary thing was not the large redshift, because at that time there were already galaxies known with much larger redshifts. The extraordinary thing was the brightness of the quasar, because it was several orders of magnitude brighter than even the brightest galaxy could appear at a distance of 1 billion light years. So it was not the large redshifts, but rather the tremendous luminosity which first pinpointed the quasars as extraordinary objects.
Given that quasars were billions of light years away, astronomers were able to infer the luminosity or intrinsic brightness of these objects. The results were astounding.
The luminosities inferred this way were perhaps 100 times the luminosity of an entire galaxy. Now that would lead one to believe that perhaps these were simply scaled up versions of normal galaxies. On the other hand, when optical astronomers started to monitor the optical light from the galaxies, they noticed that they fluctuate very significantly.
This is actually quite useful in telling us something about what the source of the quasar light is. The idea is that if an object varies, the size of the object must be somehow correlated with the size of the variation. This gives us some very important clues that the quasar is actually extremely compact, very small.
Any physical mechanism which turns off or affects significantly the energy generation within an object can't propagate faster than the speed of light across that object. You can't turn a light bulb off any faster than it takes light to travel across the size of the bulb. So that implied that this luminosity, 100 times the luminosity, perhaps 1,000 times the luminosity of a normal galaxy, was all occurring from within the central 1 to 2 light months in size. That is a factor of 30,000 smaller than a normal galaxy.
So we have in these very luminous quasars the luminosity 1,000 times the luminosity of an entire galaxy like the Milky Way, consisting of hundreds of billions of stars. But that luminosity is coming from a region which is smaller than the size of our own solar system.
Of course, something that bright coming out of an area that small, it must be something extremely powerful and extremely weird. Not only that, they're luminous in many different wavelength regimes. They're luminous in the radio, the infrared, the optical, ultraviolet, X-ray. We can study them in many, many different ways.
As new satellites fly and open up new regions of the spectrum, we find that quasars seem to have almost the same amount of power output almost wherever you look, all the way from the hard X-rays, high-energy X-rays, down to the soft X-rays, ultraviolet, optical, infrared, far infrared. And it's only right at the edge of the far infrared, the millimeter region, where they start dying away. This means some extremely broadband and energetic processes going on. Every time you add an extra wavelength, you add to the amount of power output and up the problem for how do you make that much power from that smaller space.
We may have to reduce this data in the suborbital
Once astronomers knew that quasars emitted fantastic amounts of energy, they speculated that quasars were the cores of distant galaxies. But how could such immense power emanate from such tiny regions?
I'll close it from the object and it will be at the same redshift. The quasar turns out to be the extremely bright nucleus of a galaxy. What's going on there, we believe, is a central black hole with a rotating disk of material slowly falling into the black hole. We call it an accretion disk, and an enormous amount of energy radiated in that process.
The model that we have right now is that a quasar consists of a very massive black hole sitting in the center of an otherwise more or less normal galaxy. We think that the very bright light that we see coming from the quasars actually comes from matter that is being swallowed by this black hole.
It's not clear how the active nucleus affects the galaxy it's sitting in. There have been some studies that suggest once an active nucleus goes off and starts emitting all this radiation, will completely remove the interstellar medium from the host galaxy, and it would never reform, except at a very slow rate as the stars with their stellar winds begin to refill the galaxy. And that may be one way of explaining how a quasar could turn off, because there would no longer be any fuel supply coming into its central black hole.
So the question is, what keeps the quasars going? What keeps on fueling the monster in the center of this galaxy? One idea is that it's interactions between galaxies, that if the quasar is sitting in a galaxy here, and another galaxy flies by, these objects are going to interact gravitationally. The theories suggest that large amounts of gas and stars and other material flows between the galaxies, and some of it will also be dumped into the center of the galaxy hosting the supermassive black hole. One good example of a quasar that might be fueled by interaction between galaxies is the quasar PG 1613 plus 65. You can see that the quasar is surrounded by several other galaxies, and it's clearly interacting with at least one of these other galaxies. We think that this interaction might be providing the quasar in the center of this object with enough fuel to keep it as bright as it is.
Eventually, quasars do run low on fuel and change into more normal galaxies. Billions of years ago, quasars generated the light which is just now reaching us from their tremendous distances. There are no nearby quasars. They existed only in the past.
If you want to find a quasar, you certainly don't want to look around us now. The present day is not the age of quasars. The real place to look is out to high redshifts, very distant. You need to look back well over half the age of the universe to a redshift of around 2 to find the real dense regions where they kind of swarm around. They evolve in time, we say, which means that they used to be very common and now have died away until they're quite rare.
The quasar population peaks at around the redshift of 2 when the universe was at about 7% of its current age. The record in terms of the farthest quasar that we have seen so far is 4.9. Now, quasars are much rarer objects than ordinary galaxies, and there is a fundamental question of how do quasars form in the first place.
Many people think that quasars may have formed as part of the normal formation process of normal galaxies, and in the very early history of galaxies, these quasars lit up as a part of the galaxy formation process, went through a brief period of perhaps a billion years or a few hundred million years in which this quasar shone very brightly, and then either because of lack of fuel or some other reason, this quasar gradually died out. If this hypothesis is correct, then there are lots of dead quasars around, and astronomers are actively looking for these dead quasars at this day.
This search for quasars, dead or alive, also reveals much about what lies between us and these most distant objects.
This field has a redshift of 0.4. This data is actually quite good. 1, 2, 3, 4, 6, 7 or 8 galaxies bright enough that we can measure their redshifts here from the ground with the multiple mirror telescopes.
Quasars are very valuable for studying the early universe because we can see them to great distances. On that long path, the light passes through all the matter that lies between us and the quasar. And the effects of matter between us and that distant quasar can be studied then by looking at the quasar, and we gain information about the nature of matter and space in this long, long cylinder that goes all the way out to that quasar.
There's quite a good chance that there'll be some other stuff along the line of sight to that is, in the same direction. And you start finding stuff that you had never expected existed. Clouds of hydrogen, wisps of stuff, maybe the halos of proto-galaxies at quite high redshifts. These were really unexpected and great probes of the universe.
Quasars are the objects we can see closest to the Big Bang. Not only are they interesting in themselves, being strange and weird beasts that we really do want to understand, just to understand why they exist, how they could exist, but we may be able to use them to probe the conditions of the universe very soon after the Big Bang and how we got from there to here.
Between us and the distant quasars lie many other types of galaxies with active nuclei, similar to quasars, but visibly different.
We're picking up the source about 3 hours east of the meridian, and we'll track it intermittently.
Astronomers struggle to find the relationship between quasars from the past and these other, less distant, active galaxies.
Why do we call these things active galaxies? Well, because we see a galaxy and we see a very bright spot of starlight, it looks like, in the center. Yet, when you look at the distribution of light from that central starlight peak, it doesn't look at all like starlight. It has a spectrum that has, in fact, no real defined temperature. A normal star has a particular peak in its spectrum, the distribution of light with wavelength, and an active galaxy doesn't. So it's clearly a different kind of phenomena.
Observationally, we subdivide the classes of active galaxies into several based principally on their spectra. The objects that we believe to be the most luminous in the universe and the ones which are the principal testers of all of our theories are quasars. Quasars show very broad spectral emission features. There are nearer by and less luminous objects similar to the quasars. These are called Seyfert galaxies.
The Seyfert galaxies are usually spiral galaxies with very compact and bright nuclei. They have broad, strong emission lines in the optical. They sometimes have some radio emission, but it's not outstanding. So it's the unusual nuclei, both in terms of brightness and in terms of the bizarre nature of the gas and presumably the stars near those nuclei that make them exceptional.
Most quasars and Seyfert galaxies are not strong emitters of radio waves, but there are powerful radio emitters among the quasars, and there are galaxies which are powerful radio emitters called radio galaxies.
If you could have radio eyes, you'd be able to see galaxies very prominently. We don't do that, of course, in the optical. But some very prominent objects like Cygnus A was originally discovered, Centaurus A. These are the brightest radio sources in the directions of those constellations. You get a very different picture of galaxies looking at them in the optical versus looking at them in the radio. In the optical, the light is coming from stars. In the radio emission is not coming from the stars, but rather coming from high-energy particles, electrons, which are spiraling in magnetic fields.
Radio galaxies are fairly rare critters, almost always associated with giant elliptical galaxies that put out an enormous amount of radio radiation. And that's probably an indication of a very active nucleus, which means some gravitating object, perhaps a large black hole.
Despite the appearance of a variety of active galaxies, such as quasars, Seyferts, and radio galaxies, it turns out they can be explained by a single unifying model.
A very popular idea is that most classes of galaxies represent really the same physical phenomenon, but that our viewing angle determines the observational appearance of the object. One can identify several potential components in this unified model of active galactic nuclei, quasars, and Seyfert galaxies. The first component, the central object, is a supermassive black hole, perhaps 100 million or 1 billion solar masses, which is accreting material and transforming gravitational energy into other forms of energy, which we see.
As the matter falls down into the gravitational field of this black hole, it moves very fast, and if it hits something else coming the other way, it heats up very rapidly, and that energy of motion gets transferred into heat and into radiation.
Surrounding the black hole is a disk of material, the so-called accretion disk, which is feeding the black hole, and which comes from clouds of gas which strayed too close to the nucleus. The next component would be the so-called broad emission line region. This is a region wherein clouds of gas are ionized by the central source, which are moving around at velocities which are very large, thousands of kilometers per second, and which produce the characteristic emission lines which we see in the quasars and in the broad emission line galaxies. The next component would be a dusty molecular torus, which would be a few light years in size, which could, under certain viewing angles, obscure the central region, the broad emission line region, the accretion disk, and the supermassive black hole.
And there's a ring, a sort of donut of very thick, almost like a brick wall between us and the object. So we don't really see the direct emissions from the nucleus, but only kind of indirect signs of it, such as the radio jets that come out of some of these.
While the dusty torus can prevent us from observing the core of an active galaxy, astronomers have used inventive techniques to get a different angle of view.
An extremely exciting result that we obtained observing, which ranks as one of the most exciting times or discoveries of my scientific career, is the study of an active galaxy, a Seyfert galaxy, that has the catalog number NGC 1068. This was known to be an active galaxy of a certain type, but by using sophisticated techniques involving polarization measurements, the measure of polarized light, we found that lurking in the heart, invisible to ordinary light, was a much bigger monster than anybody knew. In fact, an object that was 100 times brighter than what we saw. From the direction we were looking, it was invisible, but we were able to find mirrors located in the galaxy, that is dust clouds that acted like mirrors that reflected and allowed us to get a view of a totally hidden monster that was living completely obscured in the heart of this galaxy.
Such observations into an otherwise hidden active nucleus confirm that the angle at which we view the galaxy determines whether we can see its intensely bright and tiny core. This is also true of radio galaxies, where the activity in the core can generate radio emissions in regions extending far beyond the visible galaxy.
In the case of the radio emission, what one often sees is a very concentrated, very high brightness radio source in the nucleus of the galaxy, probably confined to a light year or so in size. On the other hand, one also sees perhaps 1 million light years in size, a very extended radio emission, and that is perhaps 100 times the optical extent of the galaxy.
The radio lobes are like ears around the galaxy. The physical mechanism of radio emission isn't completely understood, but the most accepted idea here is that the basic energy source is gravitation, that is gravity converting potential energy of stuff falling in toward a massive central object, something like a black hole or a black hole in its accretion disk, and then some fraction of that being then ejected in two narrow cones or beams.
These two radio structures are not independent. Very sensitive radio maps actually show evidence of continuous radio emission all the way from this very bright source in the nucleus out to the extended lobes. And that connecting radio emission often looks like a very thin trace along the sky.
An enormous amount of energy manages to escape almost at the speed of light in two opposite directions, skirting out two enormous jets of fast-moving particles. And it's those jets that come out with a strong magnetic field, and that is what we see.
Radio galaxies, quasars, and other active galaxies are relics of cosmic evolution. As such, they give us a window to earlier epochs in the development of the universe.
The physics of the quasar and the radio galaxy are interesting because, well, we'd like to know why they're so much more numerous in the past, at redshifts of 2 or something like that, than they are now, and whether that continues to the very earliest phases.
At higher redshift, the habitat that quasars prefer might be much, much more common than it is nowadays. In the analogy that quasars at high redshift are sort of like the dinosaurs of long ago, and the rather faint, wimpy-looking active galactic nuclei at low redshifts are like normal everyday lizards, we could say that quasars might be evolving because of a change in habitat. Their habitat is being destroyed or somehow evolving with cosmic time.
Even though most quasars are found a very long way back in redshift and in time, some manage to live longer than others, some die out quickly. Why that's so is probably something to do with their fuel supply, the supply of material they have to fall onto the central black hole. People are trying to search very hard for redshifts well above 5. If you did find a quasar at, say, redshift 10, which is an enormous number, then you're causing real trouble because we've been assuming that the black hole formed in the center of a galaxy. But by redshift 10, it's very hard to have enough time between the Big Bang and this redshift in order to create the galaxy in which you want that quasar to be. So we'd be in real trouble if that happened. That could be fun.